A register is an array of bits, and by combining registers we can create a memory bank. So a memory bank is just an array of registers. So each register in this memory bank has got a particular unique address. So we read and write to the address that we're interested in by loading the address on the address bus. So with RAM, so random access memory, it's actually called random access because we can choose to change the address at any time. We don't have to read from or write to particular addresses in order, so we don't have to read 0, 1, 2, 3, 4. We can read 28, then address 0, then address 2 million. So we can pick a random address at any time in order to read data from it. So the amount of data we can store in the memory bank, so the size of the memory essentially, is determined by the width of the address bus. So there's a particular number of bits on the address bus, and we use this formula, so n equals 2 to the power k. So n gives us the total number of addresses that are possible, and k is the number of bits. So for a very simple example, if you had 3-bit addresses, 2 to the 3, we'd obviously just get our 8 different addresses, and we know they would be 0, 0, 0 up to 1, 1, 1. So essentially the number of bits tells us a different kind of how many unique addresses we can create. So memory is usually byte organized, so that means each memory address is usually a byte is stored in that address. So it's not, each bit is not addressed individually. An address corresponds to a byte. So if it's byte organized, each memory address would refer to a particular register, and that register would be 8 bits wide and hold a single byte. So each row in the memory bank represents a byte. So in these examples here, we've got each square, each one of these bits, each one of these squares is representing a bit, so we can just store our random values, but each one corresponds to a single byte. And then this address, so here 0, 1, 2 up to n-1, that is known as a byte address because each address is corresponding to a byte. So memory can also be word addressable. So now, rather than being a byte in each particular row, each row in the memory bank represents a word and consists of multiple bytes. So for a 32-bit machine, for example, we know that. So this is going to be 0 up to 32, so that corresponds to 4 bytes. So each row in the memory bank represents a word, and in this case it'll be storing 4 bytes. So every row stores 4 bytes. But it's actually not that simple, because data is usually aligned to the start of a multiple of the word size. So here, the first row is actually address 0, and the next row is address 4, then 8, and so on, because it's actually, this is kind of byte 0, byte 1, byte 2, byte 3, and this will be whatever, 4, 5, 6, 7, 8. So the data is aligned, so it only starts at multiple of the word size. So for this example, all the addresses, so 0, 4, 8 onwards, will be multiples of 4. So now look at Endianness. So this is to do with the ordering of the bytes in each word. So if this example want to store a 32-bit word, shown by this example here, so we've got 0x, so in hexadecimal 0x, 1A, 1B, 1C, 1D. So if this was going to be stored in big endian format, so the first memory address would store 1A, so that's this first byte. The next slot would be 1B, next one 1C, 1D. So with big endian, we can see we start storing from the big end of this, because we know with the hex value, this is the most significant byte, and this is the least significant byte. So with big endian, we start with the most significant byte, and little endian, we start from the least. So for this example, it would have to be stored 1D, 1C, 1B, 1A. So the order of the bytes within these words is determined by the Endianness. So you're going to be building the RAM chip. So each RAM chip is just a memory block, and it just contains an array of registers. So the number of registers depends on the size of the RAM chip. So we can see we've got a input we put into this memory block, then we can store it in one of these multiple registers inside. So which register we store it when we've got a load bit, as we've seen before. So when this is a 1, so put a 1 in a load bit, and this the value here will go into one of these registers. So which register is actually selected depends on this. So you have to put an address on as well. So we've got our data input. So this is data. And we've also got our address. So by putting a different value on the address, we'll select essentially which slot in memory we want to store the input in. And then that is determined by this direct access logic. So this is a series of multiplexers and demultiplexers, which enables us to select a particular register. So that's when we're writing data, and it'll just be the same if we want to read the data as well. So we want the output, so if we want to read from register 0, for example, that's where load now will be 0. We don't want to load new data, we just want to output the data. So on the address bus then, we'll just put all zeros on the address bus. So select memory address 0, and the contents of register 0 will come on the output. So you're going to have to build several RAM chips as part of this. Each one's got a different size. But you need to know that each address is actually a word address, so it's not a byte address, because the fundamental register that makes up these RAM blocks is a 16-bit register, a 2-byte register. So each address for this corresponds to 16 bits. So actually for this example here, so we know for the 16K RAM, we've actually, we've got this many slots, but each slot actually stores 2 bytes. So the 16K RAM actually stores 32K of data. So it's actually very easy to build on, because you might look at that previous table and think, oh, I've got to connect up 16,000 registers, which you don't. That's just to do if you use this principle of recursive ascent. So we can start for a register. So in this case, you build a register, so this is 16 bits wide. And you can just combine 8 of these together to give you the RAM 8 block. And then we can use the RAM 8 block to build 64. So we get 8 of the RAM 8. We'll get 64, the RAM 64 chip. And we can just do this recursively. So you build a small block of memory, you use that to build the next block, use that to the next block, and so on. So you need to be wary of the ordering of these. So how it's drawn here, we'll call this top register bank 0. Then we've got the rest of the banks, that'll be bank 6 and bank 7. So in our 8 different registers, we've got registers 0 to 7. So now when that's used in the RAM 64, bank 0 is actually made up, because this, each of these registers in here is a kind of sub bank in this RAM 8 chip. So we've actually got, when you start putting these together, you've got a bank and then a sub bank. So when you're referring to the, when you're using the address to select which bank and sub bank to write to, you want to be very careful you get it correct, so you end up with a contiguous address space. So you should use the most significant bits of the address to select the bank, and then the least significant bits of the address to select the sub bank. So this ensures then that we end up with a contiguous number of adjacent locations. This means the numbering actually corresponds to the physical location. It doesn't actually matter in the grand scheme of things, so whichever order you do it in, each each slot in memory will have its own unique address. So you're not going to end up with any issues of overwriting memory and so on. So every slot is still unique, but it's just much more logical and pleasing implementation if this kind of each slot is numbered in order. So in bank 0 we want it to be 0, 1, 2, 3, 4, 5, 6, 7, and then the next bank carry on 8, 9, 10, up to 15 and so on. Because if you get those bits the wrong way, you'll find out you'll end up something like this. So that's to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. So make sure you get the order correct. So we'll look at an example now. So a 2-bit example. So you can see this is obviously the kind of decimal address. So once if we look at a particular address in binary, the most significant bits we'll use to select the bank, and the least significant bits we'll use to select the sub-bank. So you can see here, so in this example, so this will be bank 0, bank 1, bank 2, bank 3, and so on. So you can see these most significant bits, all this will give us 0. So they correspond from these, because these are all the same. And then we've got bank 1, so 1.0, 1.1, 1.2, 1.3. Again, so the actual bank is given by those most significant bits. So by doing it this way, we just ensure that we end up with this nice, logical, contiguous address space.